Quantity of heat energy absorbed. So when a system absorbs heat, its temperature changes. That makes sense. You put something on the stove, you're putting energy into it, the temperature goes up. The increase in temperature is directly proportional to how much heat is absorbed by that system. So we can say that mathematically, that the heat is proportional to the change in temperature, or the change in temperature is proportional to the heat. So to make a proportional expression into an equality, you have to put a constant in there. So you say Q equals some constant times the change in temperature. Well, instead of calling it K, we're going to call it C and give it a name. That's called the heat capacity. The heat capacity is going to have units of joules per degree Celsius or joules per Kelvin. And that's going to work out, if our heat capacity is joules per degree Celsius, and we're multiplying by the change in temperature, which is in degrees Celsius, the units cancel out and we get joules, which is a unit of energy, of heat. Heat capacity is the amount of heat needed to change the temperature of a system by 1 degree. So you've got a system and you want to heat it from 25 to 26 degrees Celsius. The amount of energy needed to do that is the heat capacity. If you have a large heat capacity, it's going to require more energy for the same change in temperature than if you have a small heat capacity. But the heat capacity also depends on how much matter you have, right? So if you think about heating some water, if you're home alone and you want to make some spaghetti, you can get out the little saucepan and just heat maybe a quart of water. It's going to boil really quickly, right? You put the burner on full blast, it's putting out a certain amount of heat, and that water will heat up very quickly. It doesn't take a lot of energy to boil 1 quart of water. If you're tasked with feeding the whole varsity football team and you've got this big vat of water, right? It can take 45 minutes or an hour with the burner on full blast to heat the water to a boil. Personal experience. Get out the turkey fryer and do it outside. It's much faster. It takes more heat because there's more water, right? That makes sense. If you want to heat something small, it's not going to take as much heat as if you heat something large. So that means that heat capacity depends on how much stuff you have. That makes it an extensive property. An extensive property depends on how much there is. The mass of an object is extensive. It depends on how much there is. So that's not always all that useful. So specific heat capacity is an intrinsic capacity of a substance to absorb heat. And this is not going to depend on the mass, because the mass is sort of figured into that. So heat capacity would depend on the amount of matter. We can get around that by using specific heat capacity. But the heat capacity also depends on the type of material. Some things heat up much more quickly than other things, and it's because of their nature. So specific heat capacity is the amount of heat needed to raise the temperature of 1 gram by 1 degree Celsius. Heat capacity doesn't specify how much. Specific heat capacity is specific. It says, okay, 1 gram, heat it at 1 degree Celsius, how much energy? That is the specific heat capacity. So we really should always symbolize this as C sub S for a specific heat capacity. We get sloppy with the little s there. My apologies. The units for specific heat capacity are going to be joules per gram degree Celsius. So now we have the gram in there. We could also specify this in terms of molar amounts. And so the molar heat capacity, amount of heat needed to raise the temperature of 1 mole of a substance by 1 degree Celsius. And we would express that as joules per mole degree Celsius. These are intensive properties. They don't depend on the amount of stuff. Both specific and molar heat capacities do not depend on the amount of stuff. Heat is extensive in that the heat capacity depends on the amount of stuff, but in these definitions, we're specifying the amount. It's like the density. Density is mass divided by volume. And so if you increase the volume, you increase the mass by the same amount. Here, if you increase the amount of stuff, you're going to increase the amount of heat by the same amount. And so that specific heat capacity is always the same. Here are some specific heat capacities for several substances. There's some elements here. These are all metals, and we see that their specific heat capacities are quite low, less than 1. Here's a couple of compounds, ethanol and water, and here's some other materials, Pyrex glass, granite, and sand. And water here has a specific heat capacity of 4.18, and I actually want you to add a 4 after that. 4.184. Why throw away significant figures? So that's much higher. And what that means is to heat the same amount of, say, lead and water, if you want to raise them both 10 degrees, it's going to take a lot more heat to heat up the water, to raise the temperature of the water, because of its high specific heat capacity. So here's an important equation. And we've got all these arrows and stuff showing you what these things are, so that makes the equation a little hard to see. Q equals mc delta T. And technically that is the specific heat capacity. So that delta kind of looks like an A, and so sometimes we say Q equals mcat, if that helps you remember it. This is an equation you need to know. Here we have Q, the heat in joules. M is the mass of the system in grams. C sub S is the specific heat capacity in joules per gram degrees Celsius. Delta T is the temperature change in degrees Celsius. What did I do? I don't know. It's gone. Is it? Yeah, oh well. So water can absorb an awful lot of energy and have a very small temperature change. And this has a big effect on our weather. Here in the Central Valley, the sun comes up in the morning in the summer, and the temperature just goes up, right? And the temperature can change up to 40 degrees or so over the course of the day. It could be 60 at night. It could be 100 in the middle of the afternoon, right? You go over to the coast, and if it was 60 at night, it might get to 70 during the day. Same amount of sunshine, what's going on? Well, the sun hits everything. It hits the ocean, it hits the land, it hits the moisture in the air, and all of the water present at the coast absorbs energy with very little temperature change. Dry air heats up more quickly. Dry dirt, concrete, these sorts of things have lower specific heat capacities than water does. So the presence of all that water moderates the temperature. And then when the sun goes down and we stop having this influx of energy, the air cools down, and now this body of water, the ocean, is going to transfer energy from it to the air and keep the air from getting as cold. So it moderates the temperature. We also use water as a coolant because it can absorb a lot of energy without getting too hot. And so we use that in our car engines to transfer energy away from these hot mechanical parts out and away so they don't get too hot. Any questions? So, how's that for a lot of words and a problem? Right. Well, let's just read the stupid thing. To determine whether a shiny gold-colored rock is actually gold, a chemistry student decides to measure its heat capacity. She first weighs the rock and finds it has a mass of 4.7 grams. She then finds that upon absorption of 57.2 joules of heat, the temperature of the rock rises from 25 degrees Celsius to 47 degrees Celsius. Find the specific heat capacity of the substance composing the rock and determine whether the value is consistent with the rock being pure gold. Okay, so there's a bunch of numbers in there. Let's pull the numbers out. Always a good strategy. So we'll pull the numbers out. I've got 4.7 grams, and I've got 57.2 joules, and I have 25 degrees Celsius, and I have 47 degrees Celsius. Those are all the numbers in there, right? And so let's label these. 4.7 is what? Grams. It's the mass, right? Gram is a unit of mass, and it even says it has a mass of. So we'll call that M for mass. And then here it's saying it absorbs this much heat. Well, the symbol we use for heat is Q. I know you'd like it to be H, but it's Q. And then we have two temperatures. So these are both temperatures, but we have to distinguish them. One is an initial temperature, one's a final temperature, right? So you read the sentence, the temperature rises from 25 to 47. So it starts at 25, it goes to 47. 25 is the initial temperature, 47 is the final temperature. Okay? So we've got M, Q, we've got T's, and we're looking for specific heat capacity. We need the MCAT equation. Q equals MC delta T. We're trying to find C. We have Q, we have M, and we can calculate delta T. So if we rearrange this equation, the specific heat capacity equals Q divided by M times delta T. Delta T, delta always means final minus initial. That's the final temperature minus the initial temperature. So the final is 47. The initial is 25. So I believe that's 22. The change in temperature is a positive number. That tells me the temperature went up. And I can use that to see, did I do this calculation right? Yeah, it went from 25 to 47, it went up, so I need a positive. If the temperature goes down, then the change in temperature is negative. So now I have all of these numbers, and I can stick them into this equation. Q is 57.2 joules. And M is 4.7 grams. And delta T is 22 degrees Celsius. So I pull out my calculator on my phone because I forgot my actual calculator today. 57.2 divided by 4.7 divided by 22. 0.55319. Let's think about significant figures. This mass had 2. The temperature ended up having 2. And the heat had 3. So this should have 2 significant figures. So 0.55. And then what are the units? Well, look at the units. Do any of those cancel out? No, they don't. So they just stay there. Joules per gram times degrees Celsius. So that is the specific heat capacity of the shiny gold rock. How do we figure out if that is consistent with the rock being pure gold? We're going to compare it to the specific heat capacity for gold. That's not something you should memorize. If you need it on an exam, it'll be given to you. So we're going to go look it up. Here's gold. Gold has a specific heat capacity of 0.128. Is the rock gold? No. Because this is much higher. This is 0.55. So, not gold. Any questions? What would be an easier way to figure out if that was gold? Density. So we got the mass of it. You could fill a graduated cylinder part full with water, make a note of the level, put the rock in the water level goes up. The difference in the water levels is the volume by displacement. You can find the density. Density is also an intensive property of a substance. It can be used to identify a substance. Any questions? So two objects at different temperatures, if they are in contact with each other, heat will flow from the higher temperature to the lower temperature until we get to the same final temperature. The heat lost by the hotter object will equal the heat gained by the colder object. So we can use that idea to help us find things that cannot easily be measured. So let's look at this scenario. Here we have a beaker of water, and we're going to put this chunk of metal in it. So this metal starts out at 55 degrees Celsius, and the water starts out at 25 degrees Celsius. So the metal is hot, and we stick it in the room temperature water. Heat is going to be transferred from the hot metal to the cold water. The metal will cool down. The water will warm up until the temperature is the same. We know that's going to happen. We know that the heat lost by the water has to be equal to the amount of heat gained by the water. And when we're writing it out with, symbols and numbers, we don't have words to specify the direction, and so we need the sign, a negative sign. So Q metal and Q water are the same magnitude, but their signs are opposite. So exactly how much this temperature changes depends on the mass of the water, the mass and specific heat capacity of the metal. Yeah, that's redundant. The specific heat capacities of the metal and of water. So the mass of the water, the mass of the metal, and the specific heat capacities. Q for the metal equals negative Q for the water. Well, Q for the metal is the mass of the metal times the specific heat capacity for the metal times the change in temperature for the metal. That must equal negative Q for the water. So Q for the water is mc delta T for water, and then multiplied by -1. It might help if you put parentheses around that. So this part in the parentheses is Q water, and the sign has to be opposite. That make sense? What's lost by one is gained by the other. It doesn't matter what side you put the negative on. If you multiply both sides by -1, then this side has the negative sign, and that side doesn't. It doesn't matter. So let's do a problem. A block of copper of unknown mass has an initial temperature of 65.4 degrees Celsius. The copper is immersed in a beaker containing 95.7 grams of water at 22.7 degrees Celsius. When the two substances reach thermal equilibrium, the final temperature is 24.2 degrees Celsius. What is the mass of the copper block? It seems like it would be easier to just put it on a balance, but maybe you don't have one. Okay, so let's draw a picture to help us think about this. After you've done a few of these, you can just kind of have the picture in your mind. But until that point, it may help to have a picture. So we've got some water, right? What do we know about the water? We know the temperature. So the initial temperature of the water is 22.7 degrees Celsius. So they told us that. Do we know the mass of the water? Yeah. The mass is 95.7 grams. So we've got the mass of the water, 95.7 grams, and the initial temperature is 22.7. When the two substances reach thermal equilibrium, the final temperature is 24.2. Is that the temperature of the water or the copper? Yes. It's the temperature of both of them at the end, right? They start at different temperatures. One cools down, one warms up. They meet somewhere in the middle. The final temperature is the same for both of them. So T final for the water, 24.2 degrees Celsius. Poor planning. Okay, so let's think about the copper and what we know about that. So we've got this block of copper. What do we know about that? We know an initial temperature, 65.4. Do we know the mass? No, it says unknown mass. And the question is, what's the mass? That's what we're going to try to find. What else do we know? What's the final temperature? It's the same as the water, 24.2 degrees Celsius. The copper cooled down, the water warmed up, but they end up at the same temperature. The temperature is not exactly between the initial of each because you have differences in mass and you have differences in specific heat capacity. Okay, so Q for the copper has to equal negative Q for the water. I'm not using subscripts, I'm using colors here. If you're doing this in pencil, you'd need to specify maybe W for water and C for copper or something. So Q for the copper is equal to Q for the water, but the sign is different. We don't need to think about which is negative and which is positive. They're just opposite of each other. Well, what does Q for the copper equal? Well, Q equals MC delta T, right? So that must equal negative Q for the water, which is MC delta T, right? So we've got the delta T's. We've got the mass of this. We want to find the mass of this. So let's rearrange this equation. I'm going to divide both sides by C and delta T for the copper. So divided by C sub S and delta T for the copper. And then I'm going to erase those from over here and move the M over. I just rearranged the equation. I solved the equation for M. So I have these delta T's where I can find them, right? It's the final minus initial. I have the mass of the water. I need specific heat capacities. I'm going to go to a table and look those up. So let's go back to the table. There it is. So copper, 0.385. Water is 4.18. So C sub S for the copper is 0.385. Units are joules per gram degrees Celsius. And for the water, C sub S equals 4.184 joules per gram degrees Celsius. I looked those up. You don't memorize those. Well, I need delta T. So delta T for, oh, I've got a blue pen going on here. Let's do that first. Delta T for the water. It's the final minus the initial. So it's 24.2 minus 22.7. (24.2 minus 22.7), 1.5 degrees Celsius. And for the copper, delta T equals 24.2 minus 65.4. 24.2 minus 65.4, negative 41.2 degrees Celsius. The change in temperature is negative. The temperature went down. Going down is negative. So now I have all the numbers, and I can plug them into this equation. So M equals negative times the mass of the water, 95.7 grams, the specific heat capacity of the water, 4.184 joules per gram degrees Celsius, and the change in temperature for the water, 1.5 degrees Celsius. Divided by the specific heat capacity of the copper, 0.385 joules per gram degrees Celsius, times the change in temperature for the copper, negative 41.2 degrees Celsius. Any questions? This is a little more complicated than the Q plus W one. Let's check our units. Gram cancels gram. Degrees Celsius cancels degrees Celsius. This degrees Celsius cancels that one. The joules cancel, and I end up with 1 over grams, which flips around and becomes grams. So now I just do the math. So I'm going to take 95.7, negative 95.7, times 4.184, times 1.5, divided by 0.385, divided by negative 41.2 equals. So I get a mass of 37.86 grams. In terms of significant figures, when we did this subtraction, we only ended up with 2. So it's got 2, and we'll call that 38 grams. If we didn't have this negative sign here, and we had this negative temperature change, we'd end up with a negative mass. Can you have negative mass? Only in science fiction books. You can't have negative mass. It's not possible. So be careful with the signs. One of these has to be negative, one has to be positive, and that sign is going to come from the change in temperature. Because one's going to go up, one's going to go down. One's going to have a positive delta T, one will have a negative delta T. Any questions? Mm-hmm. Why 2 sig figs? Good question. So when I subtracted my temperatures, 24.2 minus 22.7, that should have 1 decimal place, 1.5. Sometimes when you subtract or add, you gain or lose sig figs. So it comes from that result. I am practicing and demonstrating significant figures for you in all of the calculations I do. On an exam, doing a question like this, if it was multiple choice, I would not try to trick you with sig figs. I wouldn't give you 38 grams as an answer and 37.86 grams as an answer, because that would be trying to trick you with sig figs, and that's not my purpose. Sig figs are important, but they're not the end-all be-all. They're not the goal of chemistry. We want to have an appreciation for the significance of significant figures, that they are something to be considered. If you don't get them exactly right all the time, it's okay. Any other questions? Did that. Okay. So that was a lot of talk about heat. Need to talk about work. So one type of work is called pressure volume work. And this is caused by a volume changing against an external pressure. So if we imagine this piston cylinder assembly, and there's a gas in here, it has an initial volume, right? And if you look at the cross section, it's a cylinder, and so we've got an area here times a height equals the volume. So when that volume expands and pushes the piston up here, the piston has moved delta H, right? As this gas expands, its volume is still the height times the area. The area is the same, but now the height has expanded, and so you can measure the change in height. That is a distance, right? And a force acting on a distance is the definition of work. It requires force because there is pressure outside, normal atmospheric pressure at the very least, that the gas is pushing against. So when gases expand, the change in volume is positive because they're getting larger, right? The final volume is larger than the initial volume. But the system is doing work on the surroundings, and so that needs to be a negative number. So our definition, our equation for work here, W equals negative the pressure times the change in volume. The negative sign there is necessary to get the direction correct. So when you do things like that, if you have pressure in atmospheres and change in volume in liters, you end up with units like atmosphere liters. Like, that doesn't seem like a unit of energy. Well, it is. It's kind of a long way around, but there's, stupid pointer. I'll just put a box on it. One of these days when I have a minute of spare time, I'll figure out why my pointer doesn't work down there. It's never going to happen. So there's a relationship between joules and atmosphere liters. I would give that to you on an exam. But you need to remember that that conversion exists. That's the tricky part. 101.3 joules is equal to 1 atmosphere liter or 1 liter atmosphere. Another cylinder. Cylinder equipped with a piston expands against an external pressure of 1.58 atmospheres. If the initial volume is 0.485 liters, the final volume is 1.245 liters. How much work in joules is done? Notice they're specifying the unit here. Well, let's pull the numbers out. So we've got 1.58 atmospheres, and we've got 0.485 liters, and we have 1.245 liters. So let's try to identify these. Well, 1.58 atmospheres is the pressure. And we've got 2 volumes that are given. This is talking about the piston moving out, the volume of the cylinder expanding. So we have an initial and a final, and it actually labels them for us. The initial volume is So let's call that one VI, and the other one is the final volume. They're asking us to calculate the work. So this is pressure volume work. The work equals negative P delta V. Well, delta V, delta in front of anything, means the final minus the initial. So this is final volume minus initial volume. So 1.245 liters minus 0.485 liters. (1.245 minus 0.485 equals 0.76. Let's think about the significant figures there, though. When we're subtracting, we're looking at the fewest decimal places. Each of these volumes has 3 decimal places, but my answer only has 2. Is that good? No. This is what my calculator shows me. My calculator doesn't know about significant figures. And if you try to explain it, it plugs its ears and says la la la, so it can't hear you. It doesn't want to know about them. So we have to do this ourselves. We need to put a 0 in there, because this does have 3 significant figures. So there's our change in volume. We've got our pressure. W equals negative 1.58 atmospheres times the change in volume, 0.760 liters. Actually, I don't want to write it up there. I want to write it down here. Come on. So that's going to be negative 1.2008. And the units are atmospheres times liters. Nothing is canceling out there. I've got 3 significant figures. The work is being done, so it's negative, so that's good. But I'm supposed to give my answer in joules. So I need that conversion factor. So 101.3 joules is equal to 1 atmosphere liter. So then these units cancel out. I take that number, 1.2008 times 101.3. I get negative 121.64 joules. I still have 3 significant figures, so my final answer is minus 122 joules. Any questions?